Moving on to section 5.3, cubic and quartic equations. So a cubic equation is of the type ax cubed plus bx squared plus cx plus d equals 0, and the quartic has got the highest power of 4. Obviously, b, c, d could be zeros, but a must not be equal to 0 in either of these, because if it is, then they stop being either cubic or a quartic equation. Now you need to be able to solve both cubic and quartic equations, okay? So let's just see what happens to the solutions. So first of all, with a quadratic equation mentioned on the previous example, if you know one solution being a complex number, you know that he's a non-identical twin brother, complex conjugate, will also be the solution. Now with the cubic, here's what you can have. You can have you'll have 3 solutions. In the quartic, you'll have 4 solutions. All 3 solutions are real. So belong to the set of real values. Okay, this symbol means belong to. So this is your traditional standard 3 different numbers come out of the 3 brackets if you can factorize it. But what happens if you have a complex solution? So you could have a complex solution, one complex number, but you will also have to have his brother. So thus you will have a pair of conjugate pair. So then you've got the remaining one root left. It has to be real. So one real solution or root plus complex conjugate pair. Okay, so let's move on to quartic. So these are the only 2 situations for cubic. For quartic, you can obviously have all 4 roots or solutions being real. Now, if you have one complex number, it has to go with his brother. So you can have a complex conjugate pair plus 2 real solutions. So 2 real solutions plus a conjugate pair. And finally, you can have 2 pairs of conjugates. So 4 complex numbers solutions, they go in 2 conjugate pairs. So 2 pairs of conjugates. Okay, so we'll have a go at solving a cubic, and also solving quartic. So the first example 10, here is your cubic, and it says that -1 is one of the roots. You can call it alpha if you want to. I'll call it Z1. So in part A, we need to find the value of k. They try to make it more interesting by not writing the constant term at the end. So if -1 is one of the roots, one of the solutions, then it must satisfy this equation. So I'm going to substitute -1 into our cubic and know that it will only be the solution if I get the answer of 0 at the end. So this is going to be -1, -1, so it's -2, -3, -5, add k is equal to 0, so k is equal to 5. So then for part B, we are asked to find the other 2 roots of the equation. So this is something you do, we will do it later on in normal maths. if we know that this is one of the solutions, then you know it must have come from this bracket. That means this is a factor of the cubic. So it must be possible to put this cubic into brackets, z plus I, and then a quadratic expression equals to naught. Okay? No, yeah. But this here will be equivalent to our cubic. So let's just logically think what kind of quadratic expression would make sense to give me this cubic. So let's write this cubic down. It's got 5 at the end. So let's start with the end term and the starting term. So 5 must have come from multiplying 1 times whatever is at the end. That gives me 5. Well, it has to be 5. It's the only way I can get 5 at the end. Now, what about the cubed, z cubed at the start? How do you get this? There's only one way of getting it, by multiplying that z by whatever I put in here. So z times what gives me z cubed? Well, z squared. So I've got a big chunk of my quadratic already in here by looking at this side. So in here, I'll have, I don't know, let's have p lots of z. So we need to find what that p is. So think about it. How do I get 3z here? Let's have a look at 3z. Okay, so to get 3z term on this side, I must have multiplied that z by my pz. No, that's z squared. Okay, messed it up. And that's z by 5, and then 1 by pz. So pz plus 5z must be equal to 3z, because there's 3 of them. So p plus 5 must be equal to 3. So p has to be equal to minus 2. There you go. So our cubic must be z squared, z plus 1 times z squared minus 2z plus 5. An alternative way of finding this quadratic is by dividing by z plus 1. So I'm going to have a go at dividing it by z plus 1. I'm not doing it like the book does. You will do it later on when you do year 1 in normal maths, but you need to be able to do it with box method, not by doing long division as they show in the textbook. So let me show you, because you might prefer this way of doing it. So if you have to divide your z, let me just check it again. Okay, so what we're going to do, we are going to divide this cubic by z plus 1. So this is what I've got to do in order to find what quadratic I'm left with. So I'm going to divide it by z plus 1. There you go. So let's see whether I get the same answers before. So you do the box method. You've got to let me just okay, I've started it. Start again. Okay, so Over here, I put what I'm dividing by. Over here, I'm going to write the answer. So here is where my answer going to go. So my quadratic. Now, in the middle here of the box, I'm going to put my cubic. Because quadratic times this will give me cubic. So let's start filling in with the highest power of my cubic. So z cubed. So z times what gives me z cubed. So you know it's z squared. So you put z squared above. Then you do z squared times 1 to give you this term here. And then you know that in here, you've got to have minus 1z squared terms. At the moment, you've got one of them. So you need to adjust this amount. So you've got to put minus 2z squared. So these two add up to minus z squared. Then you're going to check how many z's in minus 2z squared. Well, this is minus 2z. Minus 2z times 1 is minus 2z. How many z's do we need? Well, 3 z's. Well, that's minus 2z, so I need to have 5z extra in order for these two to add up to 3z. Then z times what is 5z? It's 5, and 5 times 1 is 5. Okay, so the missing quadratic has to be z squared minus 2z plus 1, plus 5, sorry, which is the same as I've done before. So now, whether you use the first method, which is by comparing coefficients, or doing box method, you still have to find the solution to this equation because you've been asked to find the remaining roots. So we are going to solve when it's equal to 0. So I like to do it by completing the square. So you're going to get z minus 1 squared is equal to minus 4. So z minus 1 is equal to plus or minus square root of minus 4 is square root of 4, which is 2, and then you've got I. Moving the 1 across, you get 1 plus or minus 2i. So the three roots are 1, which was our initial one, or was it minus 1? I think it was minus 1 since I divided it by 1. And 1 plus 2i and 1 minus 2i. There you go. So this way you can, no, we need to go through example 11 and we'll be able to then, I think, move on to exercise. No. Oh, there's 2 more examples before I can move on to 1F. Okay, so in this one, we are told that in this quartic equation, you've got one of the roots is 3 plus I. This is really powerful because if you know that 3 plus I is one of the roots, then you know that 3 minus I is also the root. If you know 2 roots which form a pair of a conjugate pair, then you can work out the quadratic that these two come from. Okay, so let's use the alpha and beta method. So in alpha and beta method, you're going to put the sum of the roots in front of z minus the sum and the product of the roots at the end. So if you add the two together, you're going to get 6. If you times the two together, you're going to get the difference of 2 squares. But because you're squaring I, you end up adding those. So it's 9 add 1, which is 10. So putting these into our quadratic, z squared minus 6z plus 10 is our equation that these came out of. So this equation must also be a factor of our quartic. So let's find the other quartic that this, the other quadratic that this quartic generates. So let's do exactly the same as we did before. What would I need to put at the front and what do I need to put at the end? So the front you're going to get by multiplying z squared by what to give you 2z to the power 4. So clearly here it must be 2z squared. That's the only way you can get these. What about the constant term? It's 10 here. If I multiply 10 by whatever is at the end of this bracket, second bracket, I must get minus 50. Well, what was it? Must have been minus 5. Okay, and then here we are going to find z terms. So let me call it pz for now, so we'll do it steadily. So what is the value of p? So all you need to do is pick one of the other three that you haven't used yet. You've used the information about the z to the power 4, and you've already used the information about minus 50, the constant term. So let's have a look at z cubed. There you go, why not? Let's do z cubed. So how can I get z cubed? By multiplying these two brackets. So you would take z squared and multiply it by pz, and you can do it by minus 6z and multiplying it by 2z squared. So what's that? It's going to be z squared times pz. So it's going to be pz cubed. And you've got minus 6z times 2z squared. That gives me minus 12z cubed. But how many z cubes do we need? Minus 3z cubed. So just don't need those z cubes really. You've got p minus 12 has to be worth minus 3. So p gives me 9. So our second quadratic is 2z squared plus 9z minus 5. And the first one was z squared minus 6z plus 10. So what we need to do now, since we've been asked to find the solutions to our quartic equation, we already know this one has those two roots. We just need to solve the second one. So 2z squared plus 9z minus 5 is equal to 0. I reckon this one will factorize. 5 1, let's try it, 10 and minus 1, that should work. So the other two solutions are real. Z is equal to a half or z is equal to minus 5. So altogether z is 3 plus I, z is 3 minus I. You can name them z1, z2, z3, z4. There you go. Okay, so let's move on to example 12. We are going to show that z squared plus 4 is a factor of z to the power 4, etc. So here you could do division. So I'm going to do it in two ways. Alternatively, you can do it again by comparing coefficients and showing that you also get a beautiful, two quadratics that are perfect, okay, that it works. Well, let's just do it by dividing so you can see that how this method works again. So you're dividing this by z squared plus 4. We are going to fill in the box with our quartic. So you put z to the power 4. And then you ask yourself how many z squared in z to the power 4. So z squared, multiply that by z squared. The next term you're going to sort out is cube term. So you need to write it down. There's no cubed here, so must put it in, because the box needs to have minus 2z cubed. How many z squared in minus 2z cubed? That will give me minus 2z. Multiplied by 4 is minus 8z. The next one we're going to sort out is 21z squared. I already have 4z squared, so I need to add 17z squared. How many z squared in 17? Z squared 17. 17 times 4, it's going to be 17. 7 times 4 is 28, 68. Let's just check that we've got all the things in the box. Z to the power 4. Z cubed is minus 2z cubed, that's correct. You've got 21z squared minus 8z, perfect. So no remainder, so it's a factor. Alternatively, let's do the comparing coefficients. So z to the power 4 minus 2z cubed plus 21z squared minus 8z plus 68 is z squared plus 4 times another quadratic. And we are going to find it by using logic. So let's find the end term. So it's 4 times what gives me 68, so that must be 17. Then let's look at the start. Z times squared times what gives me z to the power 4, must be z squared. And then here we're going to do pz, and you can use cubed, squared or z term to find pz. I'm going to go for z term, put z, comparing z's it's called. So you have minus 8z from the left hand side. I don't need to put z's. If you noticed before, we cancelled them. How do I generate z's from this side? Well, to get z, I do 4 times pz, so it's 4p. And any other way of doing it? No, because there's no z term. So p is equal to minus 2, as we did here. So you found a perfect solution, therefore z squared plus 4 is a factor. Okay, so now let's just solve this equation when it's equal to 0. So we've got to solve z squared plus 4 equals to 0. That is z squared is minus 4, so z is plus or minus 2i. And the second equation is z squared minus 2z plus 17 is equal to 0. Let's complete the square. I don't think it factorizes. Minus 1 plus 17. Yeah, it gives me minus 16. So z minus 1 is equal to square root that plus or minus 4i. Z is equal to 1 plus or minus 4i. So these are the two conjugate pairs representing the solutions. So we can have a go at exercise 1F, and that's the end of the chapter.